so now these two things look very similar, except one is an infinite series, one is a finite sum. We can look at the difference. So e to the minus 1 minus dn over n factorial, which is the probability that we are interested in. So this is just sum from k starting from n plus 1, right? All the way up to infinity. So I got rid of this finite piece out of it. So of minus 1 to the power k over k factorial. Now there is a name for it again, you may remember from calculus. This is the remainder term. And the remainder term, when you have nice converging Taylor series, is going to be small for large n. And in this case, things are particularly nice. This is an alternating sum, alternating series. And it's, I don't know, alternating series theorem or something, which tells us an approximation for the error term, and it says that this is less than 1 over n plus 1 factorial, actually. So this is the alternating series estimation theorem. It's all in standard calculus. So what this is telling me basically is that the two things are very close to each other for large n. Okay? And the tail goes to 0 as n goes to infinity. So as a result, let's just e to the minus 1 and the probability dn over n factorial, the probability of getting an arrangement, the two get closer to each other as n goes to infinity. And I just want to say that for any practical consideration, we can just say that this probability is approximately 2 minus 1. Okay? Now observe that the right hand side is independent of n. In that sense, last lecture I told you that it's interesting. I mean, it's amazing that in fact this probability, whether 7 people check in heads or 700 people check in heads, the probability of getting a derangement when people receive wrong heads, everyone receives the wrong head, is essentially the same. And this number is equal to -1. Starting with n equals to 7, these two numbers agree at least to the 3 digits, so they are basically the same thing. Okay. So this is independent of n. head check problem. So we have found the answer to the head check problem. Is dn over n factorial, which is e to the minus 1 approximately, and this is approximately, is 0.68. I should also say that starting n greater than or equal to 7, these two numbers agree to at least 3 digits. Now, of course, you may say that for small n, the difference is large. So, for instance, if you look at, if you have two people, right, there is only one derangement of two people. All right, d2 is 1. 2 factorial is 2, so d2 over 2 factorial is just 1/2. The difference is huge, basically, in terms of probability, but you know, starting with 7, these are basically the same things. Already for n equals to 7. Questions? Alright, so there are some relations that this number satisfies. I'm going to just do one of them and give you the second one. Some relations, these are called recursive relations. Relations that dn satisfies. So one of them is the following things. Now, why are they good for? What are they good for? They are good for calculating dn if you know some previous dn's. So dn can be written as dn minus 1 times the sum of the previous two. Starting with n equals 3. Obviously, you need the first two here. So any recursive relation generally comes with, depending on how many terms the formula involves, you need to have either one or two initial terms. In this case, d1 is 0, d2 equals to 1. These are easy to calculate. So you see the usage of this is, you can calculate d3 easily, and then d4 and d5, etc. Even though doing it directly from the formula may look a bit harder, this makes your life easier. So this, for instance, as I said, can be used to calculate. I'll prove it, but in a second. So dn or dn recursively. Using d1 is 0 and d2 is equal to 1, for example. But you have to do it one by one. So you need to first do d3. This would be 2 times d1 plus d2. Okay, so this is 2 0 plus 1, which is 2. And then you can do now d4. This is going to be d2 plus d3. So this is one we just calculated. This is that's a 3. This is going to be 9, etc. And if 5 is 44 now, we can just, we wrote it directly there, we can just calculate it. So B3 plus B4, 9 plus okay, so why is it true? I can probably prove it using the formula, but I'm going to do it give a combinatorial proof. So namely, I'll just show you the count, dn, I'll count it through the sides. I'm sure that they count to something. Okay, so one side we know where it counts, so we'll try to count the derangements and let's see what we are going to get here. So let's write what dn is. So this is the number of permutations of the following type, right? In where I1 is not equal to 1, I2 is not equal to 2, goes like that, In is not equal to n. Okay, now, alright, let's just think for a second. So I'm not allowed to put 1 in the first position, right, in these permutations. So I can have anything else. And for this I have n minus 1 factorial, n minus 1 choices, and this is where this n minus 1 is going to come from, right hand side. Alright, so let's keep this in mind. This put aside, let's now try to split these permutations further. Alright? So in this, I have the following kind of permutations. I'm going to write a containment here because it's not going to be all of it. For all of it, I'm going to need to multiply things by n minus 1. So you can have, let's just pick one of these numbers from this n minus 1. For instance, 2. So you can have 2 in the beginning, and then you would be talking about permutations of this type. Okay? Such that I still need to have a derangement, so I3 is not equal to 3, I4 is not equal to 4, In is not equal to n. Agree? Okay, so now, but where do these things come from nonetheless? There is a list, and this list has actually 1 in it as well, even though this 1 doesn't show up here. So I have 1 here, 2 is already used, so that's the situation we are interested in. Now, this kind of permutation, now, 2 things can happen here. One of them is that the second number you pick is 1, so I2 is equal to 1, or it's not equal to 1. Okay? Now, if it's equal to 1, then what kind of permutations I'm looking at? What kind of derangements I'm looking at? So we have derangements that look like 2. So as a result, we're interested in derangements where the first one is 2, the second one is 1, and then the rest. And the rest is such that I3 is not equal to 3, In is not equal to n. Right? In this case, if the first one is 2, the second one is 1, this is a derangement still, so I need to have these conditions satisfied. But effectively, what am I counting? What's the total number of these things?
2 less than the entire duration you started with.
Hmm?
2 less than the entire duration you started with.
No, not necessarily. So total number is equal to. You were telling us.
Oh, I think you said that exactly.
No, Catherine was telling the answer.
The same thing.
The same thing as what?
dn minus 2.
dn minus 2. It's not the same thing. It's dn minus 2. I mean, it's derangement, but not dn minus 2. Right? Is it what you also said?
That's what I was trying to say.
Yeah.
I see. Sorry.
If I said it wrong, that's fine. I get it.
I misunderstood. When you said 2 less than, I thought you were literally subtracting 2 as a number. I was thinking wrong.
Yeah.
That's what I misunderstood.
Yeah.
Okay, third. Yes, absolutely. They're both correct, and this is what's said. Okay, so what's happening in this direction? Well, so then I'm looking at derangements of the following form. The first one is 2, and then I have things like that, such that I2 is not 1, I3 is not equal to 3, In is not equal to n, and derangements of what? 1, 3, 4, n, right? So what do I get total number?
Arrangement of n minus 1.
N minus 1, basically, right? So I have these n minus 1 numbers here, and I'm interested in ordering them, and they're going to come from this list of numbers, and I really want all of them to be, none of them to be fixed, so this is the n minus 1. So what we did is we looked at one particular situation where the first number is chosen to be 2, but of course you are allowed to choose any of the n minus 1 numbers from this list of 1 through n. Right? So 2 is nothing special. Anything but 1 is okay for this first position, basically. And the rest of the argument will be exactly the same for each one of them you have chosen. And this 2 will be replaced by 5. I don't know. Depending on what you do. So let's also understand that this can be any of the n minus 1 numbers. 2, 3, anything but 1, basically. So we get dn. Choose the number to put in the first position. You have n minus 1 possibilities. And then, based on whatever choice you make, do this count and get these numbers here we have. So this is again the number of choices for the first position. Some of these two parts. And this works for n greater or equal to 3, so I still need to count the first 2 of them. Well, I can do some other things with these things, which I'm not going to do anything for now. Rather, I'm going to write the second recursive formula.